Hey everybody, Trey here. Welcome to another episode in this Skew-T and Hodographs series. It's been quite a while since we did a video in this series. Had some chases in between, some other stuff I had to get done, but we are back on the wagon with this video. This is going to be part 9 of the series. In the previous video, if you recall, we discussed some common characteristics of hodographs that you might see when making a forecast. So, for example, the veer-back signature, streamwise and crosswise vorticity, etc. And now we're going to move on and actually apply that and look at some different hodographs that tend to favor different regions and different times of the year in the United States. And we're going to talk about several different types and go through where you might see them most often, what time of the year you might see them most often, and what hazards those hodographs tend to be associated with. Now, just a disclaimer before we start. These hodographs, just because I say a certain hodograph, say, is most common in the southern plains in April and May, does not mean that it can't be found in other places and other times of the year. These hodographs can happen anywhere at any time, but we're going to go through some of these hodographs and tell you where they're most commonly found and what time of year they're most commonly found. And I took a lot of information for this presentation from this article. We've talked about this article before. Cameron Nixon is one of the most knowledgeable people out there on hodographs, and this is, as far as I'm concerned, one of the foremost articles on deciphering hodographs. And I will strongly suggest that you refer to this after the video if you're kind of still confused on some of these hodographs. He's got them down here, some of them listed, and he describes them in text form. So if you're more of a learner where you need it kind of written out for you, this article is going to be great for you to look at. The link, of course, is up here at the top if you're interested. So let's get back here to our presentation. Let's get started. The first hodograph we're going to talk about is kind of what I call the classic Oklahoma hodograph. This is going to be your typical Southern Plains tornado, pretty potent tornado event. And so we're going to talk about these hodographs in terms of streamwise and crosswise vorticity as well. And we've talked about these in the past couple of videos, but just a quick refresher for you. When you have streamwise vorticity at a certain level, your storm relative wind vector, so the vector that goes from your storm motion to the hodograph at the certain level, when that vector is parallel to the horizontal vorticity vector, which is always perpendicular and to the left of the hodograph, you have streamwise vorticity. Now, when your storm relative wind vector at a certain level is perpendicular to your horizontal vorticity vector, then you have crosswise vorticity. And we talked about the fact that streamwise vorticity is much more favorable for tornado genesis and tornado maintenance. So we're going to talk about these hodographs in terms of streamwise and crosswise vorticity. So just keep that in mind when we go through these hodographs. So again, this first one I'd like to call the classic Oklahoma hodograph. This is one you'll find most commonly in the southern plains, particularly Oklahoma and southern Kansas in May. This is your classic heart of tornado season hodograph for a big tornado event. And so with these hodographs, we often see moderate to strong, mostly streamwise, low-level shear, as well as strong mid-level shear. So what this does is it promotes large supercells that tend to maintain themselves for quite a while. You can see in this example hodograph on the right here, this is from the Elmer, Oklahoma tornado event on May 16th, 2015. So you can see in the low levels here, our vorticity is quite streamwise here. This is the surface. We'll note that our storm relative wind vector and our horizontal vorticity vector are very much parallel to each other. And that's the case here through about the first kilometer or so, which we deem as the low levels. And then in the mid levels, you can see, which is our 1 to 6 kilometer level. This may not be the absolute best example of strong mid-level shear, but we do have quite a bit of mid-level shear here from the 1 to 6 kilometer layer. Decent changing of the wind speed and direction within that layer. So your main hazards with these hodographs are going to be significant tornadoes, significant hail, and damaging wind gusts. And this hodograph was associated with a pretty potent tornado outbreak across far northwest Texas into southwest Oklahoma, including the Elmer, Oklahoma tornado on May 16th, 2015. And this is another example of that classic Oklahoma hodograph. This was May 6th, 2015, which we had a long track supercell that produced a pretty long track tornado near Bridge Creek and then near Norman, Oklahoma. But you can see here, once again, streamwise vorticity in the low levels, very prominent in these hodographs. and pretty strong shear in the mid-levels. Although, again, this may not be the best example, but we tend to see a pretty decent amount of shear in the mid-levels with these hodographs. But for the most part, you often see these large looping hodographs in the low levels with strong mid-level shear. Tends to produce significant tornadoes and hail with those hodographs there. So the next one we'll go through is our classic Southeast U.S. hodograph. It's going to be your, Louisiana, Mississippi, Alabama, Georgia hodographs, typically from November to April. It's not commonly known that the kind of secondary season for severe weather in the Southeast is during the winter months, November, late fall into winter, November, December, January, February, before really ramping up again in March and April. So with these, you have extremely strong low-level shear and significant veering of the winds in the mid-levels. So that promotes strong mid-level shear. So you can see in this hodograph here at the right, this is the proximity hodograph from the Hackleburg, Alabama EF5 tornado that occurred during the super outbreak on April 27, 2011. So here's our storm motion, and you can see just a massive amount of curvature in the low levels. Very strong low-level shear, very much streamwise for much of that low-level portion there. And you can see that the winds veer quite significantly with height. So you can see here that our 1 kilometer wind is there. We go to our 6 kilometer wind, which is all the way over here. So very strong veering of the winds in the mid-levels. And this promotes very long-lived supercells with perhaps long-track violent tornadoes. And that's going to be the main hazards with these supercells. You're going to see long-track tornadoes with these kinds of hodographs. Now, you might be thinking, well, this should promote large hail as well. And that's not often the case. This is a case, these hodographs are often where we have too much shear, especially in the low levels, for large hail. And we'll talk about a typical sort of hailer hodograph here later on in the presentation. But this is going to be mostly a tornado threat, particularly a significant long-track violent tornado threat with these kinds of hodographs. And this hodograph was taken near the Hackleburg, Alabama EF5 on April 27, 2011. Here's another example from Bassfield, Mississippi on April 12th, 2020. You can see, again, very large looping hodographs, strong veering of the winds in the mid-levels. And often you'll find that these hodographs almost kind of fold back onto each other. They're almost semicircular, if you will. So we can follow here, given just the overwhelming amount of veering with the winds with height, we get these hodographs that kind of almost are semicircular. And with storm motions like this, you'll often see, we've talked about this in previous videos, that you can almost estimate kind of the shape of the storm by the hodograph. And with this kind of shape, the precipitation in the forward flank gets vented off to the east or even southeast. So the tornado is often difficult to see because it's going right into its forward flank precipitation region. And often these supercells in the southeast are high precipitation supercells. So you almost have too much shear for very visible tornadoes with these hodographs. However, does not mean that you can't get violent tornadoes. We've seen this time and time again where we have violent tornadoes, long-track tornadoes from these hodographs. Here's just another example, Louisville, Mississippi, April 28th, 2014. Strong low-level shear, strong veering with height of the winds. So our next one is called the Nocturnal Low-Level Jet hodograph, and it looks pretty similar to the Oklahoma hodograph, your classic Southern Plains hodograph. Oftentimes we see strong low-level shear, somewhat crosswise at times, but we have strong mid-level shear as well. So strong kind of veering of the winds, changing of wind speed and direction with height there in the mid-levels, amid a weaker deep layer shear. So we don't have very long hodographs per se, but we do have strong shear in the low and mid-levels. And this promotes large cyclic supercells, with the main hazards being significant tornadoes with very deviant motion, as well as significant severe hail. So these are most common in the Texas Panhandle, moving north into western Kansas through May and June. And the thing with these is that they often start out as pretty marginal looking hodographs during the day. So this is going to be our May 4th, 2007 event. This was the infamous Greensburg, Kansas EF5 tornado that occurred after dark. And what often happens in these nocturnal low-level jet scenarios is you'll see kind of during the day we have kind of these weak marginal looking hodographs for tornadoes. And then after sunset, after 0Z, the low-level jet really starts to ramp up, and you see a stark increase in the both clockwise curvature and the strength, if you will, of the hodograph here in the low levels, particularly after dark. And that makes sense because oftentimes, just in general, we often see an increase in the low-level jet after dark. And if there is a limited amount of convective inhibition remaining, this low-level jet can overcome sometimes hostile thermodynamic parameters to produce significant tornadoes well after dark. And that's what we saw with the Greensburg, Kansas tornado. This was well after dark, produced a massive EF5 tornado that devastated much of the town of Greensburg, Kansas, after dark on May 4th, 2007. And so again, that day, marginal-looking hodographs throughout the day. Low-level jet really ramps up after 0Z, and you get these large looping hodographs in the low levels, and the significant tornado threat increases, despite oftentimes hostile thermodynamic qualities of the environment. Another example of this would be the Forgan, Oklahoma tornado on May 17th, 2019. You'll notice here large looping hodographs here at 0Z at Dodge City, which is fairly close to Forgan, Oklahoma, which is in the Oklahoma Panhandle. Large looping hodographs, but you'll notice here that the overall hodograph is not that long. Oftentimes when we have strong deep layer shear, we see a lot longer hodographs. Not the case here. We do have very strong low-level shear. We were able to get a storm that produced this tornado near sunset, near Forgan, and then multiple tornadoes after dark as it moved in the general vicinity of Dodge City, Kansas. So our next hodograph is going to be what's kind of referred to as high plains magic. It's your high plains, kind of eastern Colorado into Wyoming, Montana. That tends to happen late May into July. And with these hodographs, you'll often see moderate to strong low-level shear with strong streamwise mid-level shear. So you can see here, if we take a look at our type of vorticity here in the mid-levels, you'll notice here fairly streamwise here through our 1 to 6 kilometer layer. And that often will promote pretty solid storm structure with these supercells, with also a tornado threat, perhaps some significant tornadoes in these large cyclic supercells, as well as significant severe hail. Now, these supercells, like the Nocturnal low-level jet ones, can often sustain themselves despite hostile thermodynamics. So oftentimes you don't get quite the instability that you see up in the northern high plains that you'll see in the southern plains, Oklahoma, Texas, Kansas. But you have strong shear in the low levels, strong streamwise shear in the mid-level, so you can get these cyclic, persistent supercells, even though you may have meager sort of instability. And this hodograph here was in proximity of the Capital, Montana tornado that occurred on June 28th, 2018. This is a picture of it. It was a beautiful tornado that occurred in far eastern Montana, close to the Montana-South Dakota border. And you don't get that often up there in Montana, but when you do, as well as down into Wyoming and Colorado, eastern Colorado particularly, you can get some surprise events despite these hostile thermodynamics. So our next one, kind of on the opposite end of the spectrum, but the same kind of area, is the Colorado Surprise. So this is going to be a hodograph that is characterized by weak low-level shear. You can see here in the low levels, very little curvature in the low levels, and often the vorticity in the low levels will be quite crosswise. If we do our little technique here, we draw our storm relative wind vector here to the surface, and we draw our horizontal vorticity vector, you'll notice they're almost completely perpendicular to each other. So quite crosswise vorticity in the low levels, which in general is not favorable for tornado genesis and tornado maintenance. But however, in the mid levels, we have pretty almost purely streamwise mid-level shear and vorticity. So you can see here, again, very much streamwise here in the mid-levels, which again often promotes very solid storm structure with these storms. And when you have something like the DCVZ, the Denver Convergence Zone, that occurs when you have southeasterly flow go up and over the Palmer Divide, and you get sort of this boundary that is vorticity rich. Or you have a leftover outflow boundary, for example, or you have upslope flow that creates, post-frontal upslope flow out of the southeast that creates that kind of convergence zone there in eastern Colorado. and otherwise in other areas such as southeast Wyoming, you can have the tornado threat really ramp up despite this kind of crosswise weak low-level shear. So with these supercells, the main hazard is usually significant severe hail, but you can also have tornadoes from these, particularly when low-level shear is enhanced by a boundary or a convergence zone. And they're going to be most common again in the kind of high plains region from West Texas all the way up through eastern Colorado in pretty much late May through July. And this one here was the proximity hodograph to the Simla, Colorado. Pretty beautiful supercell, textbook supercell here for Colorado. Just incredible structure with, and it produced multiple tornadoes as well. So you can see, even though you might kind of overlook this sort of hodograph when you're making a forecast, if you have that low-level shear enhancement along a boundary or convergence zone, you can get something like this, mostly a significant hail-producing supercell with several tornadoes, given that enhanced low-level shear. So the next hodograph we'll look at is the cold core hodograph. And if you watch my forecast discussions, you'll know that we've talked about this quite a bit already this year. And what we mean by cold core is you have a 500 millibar trough that generally has a closed contour there at the center, and it's associated with very cold air aloft at its center. And when you have a surface low in proximity to that 500 millibar trough, oftentimes you'll get enhanced low-level shear here on the east or northeast side of the surface low. And because you have such cold air aloft, it rapidly destabilizes the atmosphere ahead of that. And generally in these cold core events, your low-level shear is not quite as strong as a typical sort of classic plains tornado event. But because you have such strong instability, especially in the low levels, any low-level shear is efficiently stretched into the vertical, and you can get tornadic supercells, particularly just ahead, northeast or east of the surface low. You'll often get an arc of supercells right ahead of that surface low, some of which could be tornadic. And the hodograph here at the right is a pretty good example of a cold core type hodograph, where you have kind of weak to moderate low-level shear. You can see here we don't have a ton of curvature in the low levels, but your mid-level shear and generally your deep layer shear is very, very strong. You can see your 1 to 6 kilometer layer here, very strong shear within that layer. And so again, we have very kind of weak low-level shear, and that's because we're kind of removed from the strongest low-level winds. Our low-level jet usually is displaced off to the east because your surface low is kind of tucked up right underneath that cold pocket of air aloft associated with the center of that cold core 500 millibar trough. So your low-level hodograph is not going to be generally strongly curved, clockwise curved. But you have strong deep layer and particularly mid-level shear. And often there's going to be an inflection point in kind of the mid-levels, the lower mid-levels of the hodograph. And that's because, again, we're kind of removed from the low-level jet. We have kind of enough mid-level and upper-level flow to where we have kind of strong shear in that kind of upper mid-level portion of the hodograph. So you have kind of weak low-level shear, and you have a little bit of backing here in the mid-levels before the hodograph kind of trails off to the northeast or even north. And as we've discussed before, what that does is it promotes smaller, more well-ventilated supercells. So we talked about this with our Winterset, Iowa tornado outbreak case study. But again, if we kind of transpose our supercell kind of structure here on radar with the hodograph, you'll notice that in these kind of situations, your precipitation will kind of wrap around here. But then because your winds are venting that precipitation off to the north or northeast, the tornado is often highly visible because it's not moving into its forward flank precipitation region. All that precipitation is being vented off to the north or northeast. And as a result, you'll often see these beautiful storms. If you look, kind of take a step back from the storm itself, you're not so close. You'll often see these small, kind of tilted, very powerful looking updrafts. They often might be low topped because of the kind of weaker thermodynamic nature of the cold core environment. But you'll often see very, very visible tornadoes. And this was an example of kind of a pseudo cold core event associated with this hodograph in south central Oklahoma on April 22nd, 2020. It's kind of this kind of pseudo cold core event, and all your storms were kind of tilted, very viewable tornadoes. And same thing here with this example. This was on December 1st, 2018 up in Illinois. Very much the same thing. well-ventilated supercells, most of the precipitation vented off away from the tornado, so you got very visible tornadoes, kind of small, compact supercells, and this was kind of a classic cold core outbreak, and you can tell that by the hodograph. A little bit stronger shear than normal with cold core setups, but generally adequate low-level shear. We kind of get this venting, this backing in the mid-levels before the hodograph kind of trails off to the north or northeast. Again, all that precipitation is vented off to the north or northeast because of those upper-level winds. And we had strong enough low-level shear here to produce several compact supercells with tornadoes. And that's your kind of classic cold core setup. Now let's look at our kind of off-season outbreak type setup. Very similar to the cold core event, but generally stronger low-level shear. Generally stronger and streamwise low-level shear, with mostly strong and crosswise mid-level shear. So if we do our technique here, we'll do it here for the low levels here at the surface. You'll notice we have pretty strong streamwise vorticity here. But if we move off to the mid-levels here, between 3 and 4 kilometers, we'll say, we have very much crosswise mid-level shear. And that's generally the case with these off-season outbreaks. And what this does is oftentimes you're not going to see the whole storm rotate. It's not going to look like a broadly rotating supercell, but the flanks of the storm instead will rotate. And you can still, in these, despite weaker thermodynamics generally in the off-season, you can get these long-lived supercells that produce significant tornadoes and hail. Very similar to the cold core type setup where you can get tornadoes and significant hail. And that hodograph on the previous page was in proximity to the Pampa, Texas storm here on November 16th, 2015. You'll notice here that the whole storm doesn't really look like it's tilted. It doesn't really look like a supercell, except for this little flank right here, which is associated with that mesocyclone and tornado. The whole storm itself doesn't look like a broadly rotating supercell, but instead, because of that crosswise mid-level shear, you get just the flanks to rotate strongly. You can get long-lived supercells with long-lived significant tornadoes from these events. And I'm sure many of you recall the quad-state tornadic supercell from December 10th, 2021. Very similar situation. So we had very much streamwise low-level shear here, generally streamwise low-level shear. But in the mid-levels, you kind of had a little bit of backing, a little bit of crosswise vorticity in the mid-levels. Very much a similar situation. And with this one, we had thermodynamics to match, whereas in the Pampa case, we had a little bit weaker thermodynamics. With this one, we had very strong instability, very strong low-level shear. Typical off-season hodograph here, and you got a long track, very long track supercell that produced multiple long track tornadoes from it. So now let's move into the Haler type hodographs. And you'll notice here right off the bat with the difference between kind of our tornadic type hodographs and our sort of hail type hodographs is the low-level shear. You're not going to see very strong low-level shear in these cases. Generally, it's going to be very weak and mostly crosswise low-level shear. But the difference is that you have very, very strong shear in both the mid-levels and deep layer shear. So very long hodographs, but not much curvature in the low levels. And these can happen pretty much anywhere. You can get some weak tornadoes from these supercells in this kind of environment. However, significant, generally extreme, sometimes extreme hail can be the main threat from these supercells. And this one was the Amarillo sounding from May 7th, 2020, when we saw a supercell fire near Quanah, Texas, produced very large baseball size plus hail. And oftentimes, if you get some streamwise vorticity in the mid-levels, like we see in this hodograph, this is in proximity to the Hollis, Oklahoma, well-structured hail-producing supercell on April 3rd, 2019. You'll notice again, very much crosswise shear, crosswise vorticity in the low levels, but in the mid-levels we had some semblance of streamwise vorticity. And as a result, this was a very well-structured supercell, despite having very much crosswise vorticity in the low levels. And as a result, it was mostly a hail-producing supercell with some pretty impressive structure to boot. So that's kind of your Haler supercell. Again, very weak low-level shear, mostly crosswise, with very strong deep layer, particularly mid-level shear in these hodographs. And then to kind of take it a step further, this is going to be your Mothership supercell. So your best structured supercells, it's going to be quite similar to the Haler supercell, where you have kind of weak crosswise low-level shear, not much curvature in the low levels, but you have strong, pretty much purely streamwise shear in the mid-level. So you'll notice here, if we do a couple different points here on this example hodograph, very much streamwise vorticity in the mid-levels. We'll do it here at 3 kilometers as well. And we'll do another one here at 4 to show you just how much of an abundance in these situations we have. Whoops, messed the colors up there, but you get the idea. Just how much streamwise vorticity does matter in the mid-levels. Doesn't always have to be in the low levels for a supercell to be potent. If we have a lot of streamwise vorticity in the mid-levels, we'll often get these beautifully structured supercells, particularly when there's a little bit of convective inhibition in the environment, but that's for another video. We're talking about mostly the wind profiles here. So again, weak low-level shear, almost purely streamwise mid-level shear, and that promotes these large, slow-moving supercells with very impressive structure. And these are most common in kind of central and northwest Kansas, up into northeast Colorado and southwest Nebraska in May and June. And this hodograph was associated with the Imperial Nebraska supercell on May 27, 2019. Just epic structure with this storm, and that's because you had so much streamwise vorticity in the mid-levels. This did produce a couple brief, weak tornadoes, but again, that crosswise vorticity in the low levels kind of prohibits long-lived, strong tornadoes from these storms. But again, the structure is going to be the main show with this kind of hodograph. Another example here, the Leote, Kansas supercell, May 21st, 2016. This one had a little bit stronger low-level shear, but nonetheless, you can see that we had some pretty much streamwise vorticity here. Here's at 1 kilometer there, and we'll do one, say, at 2 kilometers. Not the best example here of purely streamwise vorticity, but you had enough to where you got these kind of pancake-like structure from this storm. And one final example here, this is the Douglas, Kansas supercell, June 26, 2018. Once again, weak, mostly crosswise, low-level shear. Not a ton of curvature in the low levels. Although this one does have a little bit more than some of the previous cases. But you can see mostly crosswise vorticity there in the low levels. Very much streamwise vorticity in the mid-levels here at 2 kilometers here, for example. Almost purely streamwise. So you got this kind of pancake stack structure, multiple layers, because there's a lot of streamwise vorticity in that environment. So that'll wrap it up. Of course, there are more hodographs that we could go through, but these are kind of the most common ones that you'll see when making a forecast. And again, just because we said that a certain hodograph is most common in area X at time period Y does not mean they can't happen at other times of the year in other places. These can happen anywhere at any time, but generally these hodographs kind of gave you an idea for where they're most commonly seen in the U.S. So with that, that'll wrap this video up. In the next video, we're going to take a look at the Sharp-I sounding. So we'll take a look at an SPC sounding and a model sounding, and we're going to tell you all those different variables, what all of those mean, what all the different boxes mean on those soundings, so you can really get a grasp on what parameters you need to take note of when making a forecast and what parameters you can ignore. So with that, that'll wrap this up, and thanks for watching. We'll see you in the next video.